Hello, good day. So let's start the analysis and design of spread footing. This time, rectangular footing. So when the available area requires such shapes, or when the columns cross sections are obviously rectangles, so rectangular footings are usually used. And when there is a greater load, the rectangular footing could be needed to disperse the moment and loads and lessen the soil pressure at the ends. So in general, square footings are provided under square columns, and rectangular footings are provided under rectangular columns. So it does not decrease the chance of providing a square footing under rectangular column, but it will not be economical. So same concept with the square footing, but the difference is the distribution of flexural or main reinforcement. So in rectangular footing, so we need to distribute the reinforcement in the long direction uniformly. But in short direction, a larger steel area is needed in the central portion than the far ends of the footing. So this is based on section 413.3.3.3. So it says here is that for reinforcement in the short direction, a portion of total reinforcement gamma s multiplied by as shall be distributed uniformly over a bandwidth equal to the length of the short sides of the footing. So meaning gamma s and as in short direction shall be distributed equally with the same um, same length of the short side. So centered on center line of column or pedestal, and the remaining reinforcement in the short direction. Okay, so 1 minus gamma s multiplied by as shall be distributed uniformly outside the center band. So yung gamma s natin is just equal to reinforcement in center bandwidth divided by total reinforcement in short direction. So it is equal to 2 over beta plus 1. So where beta is equal to the ratio of long to short side of the footing. So where beta is equal to the long side, or L, divided by the B, or the width of the footing. Okay. So gamma s is always less than 1. Okay. So this one is the bandwidth for steel in the short direction for rectangular isolated footing. So this is the central bandwidth B, and then this one is equal to the short side dimension. So the large percentage of load carried in hatch area, okay, and also still is the central bandwidth is greater than the outer bandwidth. So if this one is B, so the outer bandwidth is equal to L minus the total length of this is L, and then the outer bandwidth is equal to L minus B, okay, divided by 2. Same with this side. So L minus B divided by 2. Okay, so another thing, there is a difference between the effective depth in the long direction and in the short direction. So let me draw the footing, okay, for okay, so this one is for the effective depth in the long direction. So along long direction. So let's say this one is the bottom bar, and then this one is the, or this are the top bar. So the effective depth of effective depth in long direction is measured from the centroid of the bottom bar up to the outer or the upper fiber of the footing. So this one is your effective depth. Of course, this one is the thickness or height of the footing. But in along a short direction, okay, so along short direction, okay, so this will be the measurement of your effective depth. So D. So effective depth in a short direction. So obviously for when we try to compare the D requirement or D required to the D provided, obviously here the critical is in short direction. So kasi mas maliit yung ating effective depth dun sa portion na yun. So yeah. So for rectangular footing with bending in both sides, so this is the representation. So we have here the column, the dimension L and B, and then the moment along Y, and then moment along X. So F, or the pressure, is equal to P over A, and then plus minus mxcy over Ix, and then plus minus mycx over Iy. So for the simpler equation, given here the dimension, so pinross out na natin yung moment of inertia along X and I. So yung formula natin for rectangular footing is P over B squared plus minus, it should be P over B multiplied by L, then plus or minus 6mx, then B squared plus minus 6my B squared, so B L squared. Yan. Okay, so let's have an example problem. Okay, so a 600 by 600 column carries a total live load of 1,350 kilonewton and a total dead load of 1,680 kilonewton. So the column reinforced with 825 millimeter diameter vertical bars to be supported by a rectangular spread footing whose width is limited to 3.2 meters, and whose bottom is 1.8 meter below the ground surface. So allowable soil bearing capacity at the base of the column or footing is 230 kilopascal. Then the weight of the soil 16 kilonewton per cubic meter. Above the footing, and then gamma c, or specific gravity of the concrete is 16. So sorry, it should be 24. Okay, 24 kilonewton per cubic meter. And then FC prime 28 megapascal, and use 25 millimeter bar and 75 millimeter clear concrete cover. So design and draw the details of the footing using NSCP 2015. So first, footing detail. So this one is your NGL, then the applied load P. So PDL and PLL, then 1.8 meter below the ground surface. Then our planned, okay. So it is restricted to have or limited to a width of 3.2 meters. And then your length is variable. So the column is 0.6 by 0.6. Okay, so let's solve. So first, step 1 again. So for the solution, step 1, so solve for the P and PU, factored and factored load P. So P is equal PDL plus PLL. So given 1,350 and then 1,680. So 1,350 plus 1,680. So it is equal to 3,300 kilonewton. And then for PU, so usually the governing load combination is the 1.2 PDL and 1.6 PLL. So this is equal to 4,176 kilometers. So you can try to solve for the load combo 1, yung 1.4 PDL. Pero usually nag-govern na yung second load combo from NSCP. Then step number 2, assume HC or compute the initial HC. So first, neglecting the height of the footing. So yung HC natin muna is equal to 0. So the initial QE again is Q allowable minus gamma C multiplied by HC minus gamma S, HS, and then the surcharge. So cancel out muna natin yan, and then the Q allowable given 230, and then if the height of the column is neglected, or sorry, if the height of the footing is neglected, so our HS here is equal to the depth of embedment. So 1.8 yung depth of embedment natin, and then multiply by the specific gravity of the soil. So 16 And then, wala tayong surcharge. So, yung QE natin, initial QE natin is 201.20 kilopascal. Okay? Then, initial area footing. So, simply, AF is equal to P over QE, or unfactored load over equivalent soil bearing pressure. Okay, unfactored load natin is 3,330 divided by 201.2. So, result is 15.06 meters squared. Okay, so to get the value of L, kasi restricted na yung width natin ng 3.2 meters. So, area footing is simply L multiplied by its width. Okay, so L is unknown, and then width is equal to 3.2. So it is equal to 15.06 meters squared. So our L is 4.706 meter. So let's say 4.8 meter. So this should be your initial length of the footing. Okay, so now we can get the QU, or ultimate or actual effective soil bearing pressure. So QU is equal to PU, or ultimate load, divided by the area of footing. So in this case, kung ano na yung ni-round up natin na dimension of footing, yun na ilalagay natin dito. So 4.8 multiplied by 3.2. Okay, so 4176 for our PU, then divided by 4.8 times 3.2. So our QU here is 271.875 kilopascal. So now, considering one-way shear or wide beam shear, same lang yon. Okay, so first in long direction, so we need to check both sides of the footing. Okay, so draw natin muna. So in long direction, ganito yung itsura nung ating critical path. And dito sa side na to. Okay, so again, the critical or the shear path is at the d distance from the or located at the d distance from the face of the column. So this is your area of consideration, and then the width of this area is, okay, so this one is 4.8. okay, so this one is D, and then this one is 0.6, the dimension of the column. And then the value of this dimension is 4.8 minus 0.6 divided by 2, then minus the D. Okay, so simplify here. So 0.6 for 4.2 divided by 2 is 2.1 meters. So 2.1 minus D. Okay, so solve for VU. So VU is equal to QU multiplied by 2.1 minus D, the area. Then this one is 3.2. Okay, so intensity and then the area. So VU is equal to 271.875, 2.1 minus D, then multiply by 3.2. Okay, so that is for VU. And then for VC, okay, so VC, short or one-way shear beam action. So 1/6 lambda square root of FC prime BWD. So 1/6, let's say this one is a normal weight concrete, and then square root of FC prime, or FC prime is 28, and then BW here is 3.2, then multiply by D. Okay, again, this term is called the area to be sheared. Okay, so this one is the area to be sheared. So this is that area. Okay, so now we can compare the phi BC, or the capacity, with the reduction factor, with the actual or ultimate shear. So copy ko lang yan to, copy, and then copy, then paste, then multiply it by 0.75 for our phi, and then this one, copy, paste. Okay, so based on the computation, so D is equal to 0. Sorry. Okay. Copy, move. Okay, so kulang tayo ng 1,000 dito for unit, or to have a uniform unit. Okay, so our D here is 0.61172 meters, or equal to 611.732 millimeters. Okay, so now for in short direction tayo. So in short direction, okay, so along short direction, so our critical path is in or along short direction. So this one is the distance, this one is T, and then this one is 3.2. So this one is equal to 3.2 minus 0.6 divided by 2 minus D. Okay, so simply 1.3, so 2.6 yan divided by 2, so 1.6 minus D. Ayan. So okay, so our VU is equal to, okay, so equal to QU multiplied by 1.6 minus D multiplied by, So in this time, our B here is okay. Our area here is this one, and so our length or our B here is our length, so 4.8. Okay, so QU again 271.875, and then 1.3 minus D, and then this one is 4.8 meters. Okay, set it aside. So BC is 1/6, then lambda square root of FC prime BWD. Okay, so get the area or area to be sheared. Ito yon. So with a depth of D, yan. So yung depth niya is D. Okay. So this is equal to 1/6, 1 square root of 28. Okay, multiply by BW is 4.8. And then D is D. Multiply by 1,000. Baka makalimutan pa natin. So, lagay na natin din yung 1,000 dito. Okay. So, again, VBC is equal to VU. So, let's copy the equation for VU. And then copy the equation for VC. Then add the phi value or the reduction. Okay, sorry. So the reduction factor. Multiply it by the reduction factor 0.75, so equal. So our D here now is 0.378691 meters equal to 378.691, okay, millimeters. So based on the dito pa lang sa wide beam shear, makikita na natin kung sino yung critical. So the critical in terms of wide beam failure is this one, 611. And ko-compare natin yan later dun sa punching naman. Okay, so now considering two-way shear or punching shear. So again, dodraw na natin muna. This is your column, and let's say this is the shear path. Size of the column is 0.6 and 0.6 by 0.6. So again, the location or the distance of the critical shear path is D/2 distance. So dalawa yan. Okay, so dalawang D/2. So D plus 0.6. Also here D plus 0.6. Okay, so this one is 3.2, and then itong side naman nito is 4.8. So for VU, so BU is equal to QU. Then the area of consideration here, so magkakaroon ng uplift pressure is this one. So the resisting area. So yung area natin here is the simply B multiplied by L and times width minus, okay, the area, unhatched area dito, nasa loob. Okay, so minus D plus 0.6 squared. Okay, so kapag iba yung size ng column natin, iba rin yung formula na to. Hindi siya magiging squared. So this is equal, so VU is equal to 271.857, then 3.2 multiplied by 4.8 minus D plus 0.6 squared. Okay, then for our VC, so table 422.6.5.2 tayo of NSCP 2015. So tatlo yung ating VC dyan. So the least between those three. Okay, so i-copy na natin or i-compare na natin yung VBC to VU. Okay, so for using equation A, yung may lambda, okay, so phi is 0.75, and then the equation here is 1/3 lambda square root of FC prime BOD. Yan yung ating equation. So compare na natin yan. So ito siya, 0.75, 1/3, then lambda is 1, then 28 FC prime. Our BO here is the perimeter of this one, the area to be sheared. So apat na ganito, so apat na D plus 0.6, so 4 multiplied by D plus 0.6, then multiply it by D, then multiply it by 1000, then equal to this equation. Okay, so our D here is equal to 0.597,503 meter or 597.503 millimeters. Then next, for using equation B, so our equation B here, phi na to, no? Phi and then the equation. So lagay ko na yung 0.75, and then yung VC natin is 1/6 1 plus 2 over beta, then lambda square root of FC prime BOD. Then again, equate it to our VU. And so 0.75, 1/6, 1 plus 2. So our beta here is the ratio of the dimension of our column, short over long. Okay, so 0.6 by 0.6. Okay, then lambda is 1/28. BO is the perimeter multiplied by 4 multiplied by 0.6 plus D, then D, and then 1,000. Okay, so ayan yung itsura niya. Okay, so using equation D, B, so our D here is 0.460025 meter. So 460.003 millimeters. Okay, then next using equation C. So ito na yung may alpha. So depende yun dun sa location of your column. So our equation here is 0.75 or phi, and then yung VC natin 1/12, 2 plus alpha SD over BO, then multiply by alpha lambda square root of FC prime BOD. So again, 0.75, 1/12, 2 plus, so our location of our column is interior, it is a interior column. So alpha is equivalent to 40, 40D. So kapag edge 13, then kapag corner is 20. So BO, so 0.6 plus D. And then lambda square root of 28. Then again BO 0.6 plus D multiply by D multiply by 1,000. Yan. So equal to this view. Yan. So solve it, isolate the D, then D here is equal to 786 meters, or 446.786 millimeters. So compare the all of the result of D. So the maximum or the critical D here is, so 500, no, pinakamalaki, sorry, 600. Okay, this one 611.732. So therefore governing D is equal to 611.732 meters. Okay. So next, step number 3. So compute, or considering the computed initial HC. So HC, let's solve for HC. So using D, so HC is equal to D plus 75 then plus 1.5 of dB. Kapag HC yung kinukuha mo, always yung malaki, no? Lalakihan mo yung HC mo. So 1.5. So parang ganito siya. Yung ating D is located at the top of the centroid of the top of the bar, reinforcement bar. Okay, so kaya naging 1.5 to 1.5 dB. Then this one is CC. Okay, 75. So HC is D is 611.732 plus 75 times 1.5 multiplied by 25. So HC is 724.232. So let's say 750 mm. Then step 3 niya, using HC 750 mm. So our QE now is equal to Q allowable 230 minus 24 multiplied by HC 0.75, then minus 1.8 minus 0.75. Okay, so ma-minus natin dun sa embedment, depth of embedment yung ating concrete. So para makuha natin yung HS, and multiply by 16, then 0. So QE now is 195.20 kilopascal. So area footing is equal to P over QE. So 3,030 195.2. Okay, 15.523 meter squared. So again, 3.2 restriction for our width, then multiply by L is the area of footing. So L is equal to 4.851 or simply 4.9 meters. Okay, and then QU is equal to PU over 4.9 multiplied by 3.2. So PU is 4176, 4.9, 3.2. Okay, so QU is 266.327 kilopascal. So now, in long direction, kunin natin yung mga D provided. So in long direction, D provided is equal to HC minus 75 minus DB over 2. Okay. So in this case, yung ating D is D over 2. So this is in long direction. Okay. So sa long direction or along long direction, okay. So nandito yung D natin. I'm sorry. So nandito. Nandito siya. Okay, so dito. Ayan. Centered of the bottom. D. Nandyan siya. Okay. So, kung mapapansin ninyo, yung D provided natin dito, okay, minus natin yung D over 2. So, D provided at the long direction is greater than, okay, 25 over 2, 662.50 millimeter. Okay, compared dun sa short direction. So sa short direction, so actually kahit hindi mo na kunin to, yan, kahit hindi mo na kunin to, okay, so mas critical tayo dun sa yung pinrovide mo D na mas maliit. Okay, so yun yung nasa short direction. Okay, so kung do-draw uli natin yan, so ito yung ating okay, short direction. Yan. Yan, along short direction. Okay, so yung D natin dito is nandito. Okay, at the top of D. Yan, yung D. So, yung D kasi ko-compare natin sa D required. So, dapat yung mas maliit yung ko-compare natin. So, in short direction, okay, usually yun na lang kinukuha. Okay, kasi nga, yung pinang-minus natin na okay, diameter is 1.5 of the diameter of the bar. So, HC minus 75 minus 1.5. Ito. Yan yung 1.5 dB. Dito kalahati lang. So, sa centroid to. So, sa kalahati lang siya. So, mas liliit yung D provided mo. So, ito yung mas critical. So, yung D provided natin dito is 637.5 millimeters. Yan. Okay, so considering one way yung kanina. Okay. Okay, so VU, kasi yun yung nag-govern kanina eh. Yung one-way shear. So, one-way shear along long direction. Okay. Okay. So, formula natin doon, long direction. Okay, this one. So, pero, yung magbabago lang dito is yung QU natin. Okay, so yung QU, initial QU natin yan. So, yung QU na na-compute natin for D required is okay. So, yan. So, VU is same term. Pero yung QU natin, ito na yung gagamitin natin QU. QU is 266.372. So, 266.372, 327, 2.1 minus D times 3.2. So, this is your VU. And then, for our VC, okay, so yung VC natin, same lang. Okay, kasi wala naman tayong QU na binago doon. So, kung ano yung QU na VC natin, so, VC 1/6, yung nag-govern, wide beam, FC prime, BWD, so 1/6, 1, square root of 28, and then BW natin dito is 3.2. Sa long direction tayo, or along long direction, and then D required na to. Yan, ito yung D required. Ito yung ko-compare natin sa D provided. Then multiply by D, multiply by 1,000. Okay. So copy. And then paste. Okay. So multiply it by 0.75. And it equals to this 1. So D required is equal to 0.6. So this is phi BC na to, no, is equal to VU. So 0.617186 meters or 617.186 meters. Okay, yeah. So, required versus provided. So, required is less than, okay? So, required is less than the provided. So, okay tayo dun. Okay.